Cathode is negative, anode is positive. Electrons shoot across, they hit the target, and what happens when those electrons hit those tungsten atoms at the target? They create X-rays. And then the question is, how? So, when the electrons do reach the target, they go about 0.5 millimeter deep. They don't actually go that far. So, our X-rays are made in this region, right? They hit the target, they go about 0.5 millimeter deep inside that 0.5 millimeter strip all along our target, right? Our focal spot, that is where the X-rays are made. There are two things we're going to be talking about, two methods or two interactions. Number one is characteristic, and number two is Bremsstrahlung. Bremsstrahlung.
Is it?
Bremsstrahlung. Bremsstrahlung, that's right.
Spell it.
Let me know.
I read the chapter, but I was like fumbling with that word.
Okay, so
Is that good?
Bremsstrahlung is German. You know it's German because it's long and there's a lot of consonants in there. So, to make it simple, you can just call it
No, put it here?
Brems. Brems interactions. Right, but the full name is Bremsstrahlung. Now, remember, most interactions at the target do not result in X-rays. Right? Only 1% of those interactions will actually give you X-rays. 99% of those interactions produce heat only. Right? They produce heat instead of X-rays. So, X-ray production is not very efficient. Right? We shoot across all these electrons, but only a tiny, tiny, tiny fraction of them actually produce X-rays. And remember, only a tiny fraction of those X-rays produced actually travel in the correct direction, right, towards the patient. A lot of them are going to travel elsewhere. What do we call that kind of radiation? No, leakage. Remember, in the tube, it is leakage radiation. In the patient, once we get to the patient, that's when we have our scatter. Okay. So, the first thing we're going to talk about are these characteristic interactions. And so to talk about characteristic interactions, we need to talk about binding energy. So, what is binding energy? Reagan, how would you describe binding energy?
That's a good question. Okay.
Did you have anything in your note cards or your flashcards that can help you?
Oh. I really need to think about that.
We don't have that term.
Yeah, that's true.
There's no electron binding energy in your flashcards? Really? Okay. Oh, what are the, let me see the list of.
Yeah, beam quality,
Beam,
beam quantity,
Bremsstrahlung,
Bremsstrahlung.
Oh,
Oh,
okay. Huh, I didn't realize that. I thought it was in there. Okay.
Yeah, I don't know what that is.
So, just based on the name, what does the word binding mean?
like together, comes together.
Whoa, okay.
Oh.
I heard hold them together, which is great, right? So binding, right? Holding things together. So the energy needed to hold things together. In this case, it is the electrons which are being held to the atom. Okay. So the stronger the atom holds onto the electron, the greater the binding energy. Yes, Jay.
So it's basically the mass of the protons is what's keeping the electrons close to it.
So not mass,
Well,
right? So let's take the solar system, for example, right? What keeps the planets bound to the sun? Gravity, right? But this is not gravity, not inside the atom. Right? Too small scale for gravity. Instead, what do we have inside the atom?
Protons.
Protons. What do we have outside the atom?
Electrons.
Electrons. What is the charge of the nucleus?
Positive side.
Positive, right? Protons are positive. What's the charge of an electron?
Negative.
Negative. What happens if you have a positive and a negative?
Attraction.
They are attracted, right? So that is where our electron binding energy comes from, right? The electrons are attracted to the nucleus, right? The nucleus wants to pull on that electron. So of course, the closer it is to the nucleus, the more strongly the nucleus is able to grab onto it, right? The further away it is, the harder of a time the nucleus has to hold onto it, right? Because there's all this stuff in the way. So it has a tough time grabbing onto this electron, right? It's still there, but the binding energy, its attraction to the nucleus is going to be a lot weaker, right? So the closer it is, the higher the binding energy. The further away it is, the lower the binding energy. Now, as you can see, the electrons are arranged in these rings, right? We call these shells, right? The electron shells of the atom. So this innermost shell, we call this the K shell. So the innermost one, this red ring, that is the K shell. Electrons in the K shell have the highest binding energy because they are the closest to the nucleus. So if we look over here, what is the binding energy of the K shell?
69.5
Kilo
kilo electron volts.
Great, 69.5 kilo electron volts. Do you need to memorize this number?
Probably so.
Yes.
Yes.
Feel it in my spirit.
This one you need to know. 69.5 is a number you need to memorize.
Just only the K shell.
For the K shell.
Only the K shell.
Only the K shell. Yes.
The reason why it's tungsten is because of what the tube is made of, or like the inside glass.
Right. So the reason we're talking about the tungsten atom here, right, these are tungsten orbital shells, is because they are the atom that we are using for our X-ray production, right? High heat resistance and high binding energies. Something like molybdenum, right, would have a different binding energy. It's going to be lower because the atomic number is not going to be as high. So keep in mind, this binding energy here is specific to tungsten, specific to tungsten's K shell. If it's a different atom, the K shell would have a different binding energy, right? If it's carbon, it's going to have a much lower binding energy, for example. So you do need to memorize the tungsten's binding energy for the K shell. So do you think you need to memorize L shell? No, I'm not going to ask you to memorize L shell. M shell, N shell, O shell, P shell, no. You don't need to memorize those. But memorize your 69.5 because this number will be very important for everything that's about to happen. So, once again, what do you call the innermost shell?
K shell.
K shell, very good. How many shells do you see tungsten have? Great, 6 shells, right? So as you can see, we just go down the alphabet, right? K, L, M, N, O, P.
Wow, there's only 5 below it stops. Or but you have that in P.
You have 6 shells. So, which shell has the lowest binding energy?
P shell.
P shell, the outermost shell, right? If you had, okay, so if you want to remove an electron from this atom, which shell do you think would be the easiest one to remove an electron from?
P shell.
Why the P shell?
Because less power will be required.
Right, less binding energy, less attracted, so less power needed to remove that electron. Very good.
So what is binding energy?
So binding energy is just how tightly the atom wants to hold on to that electron. So the closer it is, the more the atom wants to hold on to the electron. The farther it is, the less the atom wants to hold on to the electron. It still wants it, just not as much, right? It's kind of like if, it's like ranking favorites, right? It's like K shell is where its most favorite stuff is, P shell is where its least favorite, kind of favorite stuff is, right? Still its favorite, still likes it, but not as much as the K shell. Right? So, for me, it would be something like, sushi, steak, asparagus, I don't know, chocolate, right? I kind of like chocolate, but not going to be my most favorite thing. So, I also want you to think of binding energy as, all right, so for me, the way I like to think of binding energy is in terms of money, right? Because this idea of money will kind of make things make a bit more sense later on. Binding energy is like money. This is how much money I would need to
Remove the
pay
electron.
to kick someone out of their house.
So it's like that little,
It's the same thing.
Like the Compton.
The atom, the electron.
Yeah, with the Compton
Yeah.
scatter
Right,
and stuff.
like with the Compton, that's
Yeah.
right. Just like with Compton. So, very similar concept here. Okay, so, innermost shell, gonna need a lot of money to kick that electron out of its home, right? Outermost shell, not gonna need that much money to kick it out of its home. So, our focus is gonna be on this innermost electron for characteristic interactions. So these happen when X-rays knock out an orbital electron from the atom. The electron which comes in from the filament must have a higher energy than the electron's binding energy. And what determines the energy of our electrons?
The one that's coming to us.
Yes, the electron that goes from the filament to the target, from cathode to anode. What determines the energy of that electron?
The
The
KVP?
repulsion between the two electrons.
No. Mansi, did you have a guess?
KVP.
KVP. Okay. KVP, your kilovoltage peak. Your kilovoltage is your potential difference between the cathode and the anode. So the greater your KVP, the more negative your cathode, the more positive your anode, and the more the electron will want to jump across. The more it wants to jump across, the more energy it will have. So yes, the KVP is responsible for the amount of energy the electron will carry. So, jumping back to this here. Imagine our KVP is 60. 60 KVP. How much energy will that electron have? 60. If our KVP is 60, how much energy will that electron have?
60?
60. That's right. If our KVP is 60, the electron will carry 60 keV. Does that make sense? So all of the electrons jumping across have 60 keV. And they come over here and they start crashing into electrons in tungsten. If this electron crashes into the P shell, does it have enough energy to kick out the P shell electron?
Yes.
Yes, because 60 is greater than 0.008. What about the O shell,
Yes.
N shell,
Yes.
M shell,
Yes.
L shell,
Yes.
K shell?
No.
Not as, not.
Wait, why not the K shell?
Because it's
69.
very high.
kilo electron.
That's right. So only 60 keV in my incoming electron. Binding energy is 69.5. I do not have enough energy to kick out this electron. So what KVP do we need at minimum
70.
to kick out that K shell?
69.6.
5 plus.
All right, so technically 69.6, but you can't set that.
70.
So 70, right? So 70 kVp is the minimum energy, right, that you can set in order to knock out this K shell electron. Does that make sense?
Yes.
Right? So the filament electron must have a higher energy than the orbital electron's binding energy in order to kick it out. Right, so let's say that we do manage to kick out that K shell electron. So 70 keV comes in, it's enough to kick out the K shell electron, and now there is a space where that electron used to be, right? There's an empty house now, right? In a pretty nice neighborhood, right? That's why it was so expensive in the first place. So you got this empty house in a nice neighborhood. Do you think there's going to be people wanting to move in?
Yes.
Yes, so now you've got electrons from the same atom that want to move into this nice house. Right, so the electrons from the other shells, the L, M, N, O, P shells, they see this open house in the K shell and they say, I want to move into that house. Well, in order to move in, they're going to need to pay, right?
Yeah.
They're going to put down some money. And so, the amount of money that they're going to need is the difference between the cost of the house minus how much they can sell their own house for, right? So, if we go back here, let's say the L shell wants to move in. How much does this L shell need to pay to move into the K shell? Does it need to pay 69.5?
No,
58.4.
57.4.
That's right. It's already got some money, right? It doesn't need the full price, so it can sell off its house to move in. So the amount it pays is the difference between them. 69.5 minus your 12.1. So I did hear it. It was 57.4. Right. So the amount of energy it needs to pay is 57.4. Okay. And when it pays, it actually just shoots the energy out into the void. Right? In what form does energy take? How does energy travel? So yes, what is the packet of energy called?
Photon.
A photon. So our L shell electron, when it's ready to move, takes its 57.4 keV worth of energy, packs it in a nice little box, prints the name photon on it, and ships it off so that it can move into the K shell. And that 57.4 keV photon is an X-ray. And that is where an X-ray comes from, right? That is where we get our X-ray. X-rays are formed when an electron jumps into a lower shell. Does that make sense?
Lower shell or higher shell?
So the
Lower shell. The closer it is to the nucleus, the lower it is.
Oh.
So inner shell, I guess I
Oh.
should say. It happens when an outer shell wants to jump into an inner shell. Yes, Charo.
so when the outer shell electron jumps into the inner shell electron, the energy that's released is what creates the X-ray.
The energy released is the X-ray.
Thank you.
Correct. Okay. So any questions on that concept? When the electron jumps from an outer shell to an inner shell, it creates an X-ray. Yes, Sindhu. Okay.
So from outer shell, you have to reach all the way inner shell. So do you, so each time there's energy difference or?
Right, so let's say we've got our L shell here.
Uh-huh,
Okay, let's say that this electron leaves. So now there's an opening.
right.
L shell says, I want to move in. So for the L shell to go from here to here, it needs to give off energy. How much energy does it give off?
69.5 minus 12.1.
Correct, it's the difference here. And so that difference, that energy given off, is our X-ray. Yes, Cody.
So can something from like the O shell jump all the way to K? Or does it have to go for each one first?
Very good question. So, it does not need to go in order, right? From the O shell here can potentially skip the line and jump all the way to the K shell. So, in that case,
Need more
if the
money.
O shell jumps into the K shell, how much energy would that be? A lot, yes.
Like 61 point something, right?
69
69.
4,
Maybe like
402.
68 point something.
All right,
69.42.
very close. It's 69.42.
Oh.
69.42 kiloelectron volts. So the farther away it is, right, the further it needs to move, the more energy it gives off. Does that make sense? Right, so, you know, cheap house, right, can't sell it for much, so it needs more energy in order to move in. Yes, Cody.
I don't know if this matters, but why would you choose the one shell over the other? And like, can you even target one shell over the other?
All right, great question. So we are not able to control what happens inside the atom, right? We can't even control the fact that the electron will hit the K shell. It is all luck. So in order to get lucky, we just throw millions of electrons at our target and hope some of them kick out this K shell electron. When it gets kicked out, it's pure luck as to which one jumps in. The closer ones are more likely to jump in, but there's still a chance the further ones can jump in, right? Ideally, we would like the further ones to jump in, so our X-ray energy is higher.
That's what I was getting ready to ask.
Mhm.
So I was gonna ask you that. I was gonna ask, so that energy, that, the difference in the energy
Mhm.
between the two shells is what the energy of the X-ray is.
Correct.
Okay.
Mhm. So as you can see, we can create all sorts of different X-ray energies now, right? If this is the jump, we can create an X-ray with about 57 keV. If these are the jumps, we can create energies of like 69 keV. We can get different energy X-rays out of our characteristic interactions, just depending on which one jumps down into the K shell.
So the difference is the X-ray.
The difference in energy is the X-ray, yes.
The filament electrons, or you're just saying like when the thermionic emission comes and then one of the electrons is coming in to the atom? Basically?
Correct. So over here is the filament. The filament shot an electron over here to the target. So the electron came to the target, got lucky, hit the K shell, and it had enough energy to knock the K shell electron out of the atom. So we have that hole, and now any of these electrons can jump down into the hole. Now, let's say that the L shell does jump down. Well, now, what happened to the L shell?
It's vacant. It's empty.
Now there's an empty house in the L shell, right? What do you think these electrons want to do?
Jump into that one.
Right, they want to move in, right? It's not the K shell, but it's still a pretty nice neighborhood. All right, so now M shell says, I see there's an opening. I'm going to move into that house. When it moves, what happens?
It's gonna need like
So
10.
the difference 1.7, 1.
Okay, yes, so it's also going to give up some energy to move into the L shell.
1.
So now the M shell is empty, right? We've got an opening here. What do you think happens?
The N wants to move.
N wants to move in. Okay, there's an opening here. What do you think happens? O wants to move in. There's an opening here. What do you think happens? P wants to move in.
But you said it's not only step by step, can anything else can move in also.
Correct. So M is open. Maybe O gets lucky and it jumps the line, right? Maybe P gets lucky, it jumps the line. But you set off this sort of chain reaction where once you have an opening, electron jumps in, leaves a new opening, electron jumps in, leaves a new opening. And so you have this giant chain reaction of electrons moving and creating X-rays.
So it's like a cascade effect?
It is a cascade effect. Very good. And that is what we call
Characteristic
our
cascade.
characteristic cascade. So that is literally called characteristic cascade. So as you can see in this diagram, right, you can have electrons jumping in from outer shells, right, any of these outer shells into the K shell. Or you can have any of these electrons jumping into the L shell. You can have any of these electrons jump into the M shell. But it's more likely that the closer it is, the more likely it is to jump in. So this is our characteristic cascade. Electrons jump, leave an opening, electrons jump, leave an opening, electrons jump, leave an opening. Every single time they jump, what do they give off?
Energy.
Energy. And that energy is our X-rays.
And then also characteristic radiation or something? We were
Mhm.
talking
So,
about that before.
That's right. Another term for this is our characteristic radiation.
So X-rays are also called characteristic radiation.
Only when produced through our characteristic cascade. Because remember, this is only one way to create X-rays. There's still a second way, right?
Oh.
Our Bremster law. Right? But this is one way we can create X-rays.
What was the second distance? Sorry.
Brems. Bremsstrahlung. So why is this called characteristic? It's because it's based on the character of those electron shells, right? If it jumps from L to K, the energy difference is the same every single time, right? So the X-ray you get out is going to be the same energy every single time. Does that make sense? If it jumps from the P shell to the K shell, that difference is the same.
Every single time.
Okay, everyone?
Every single time.
Great, every single time. So the X-ray created has the same energy
Every single time.
every single time. Right? So that's why it's characteristic, right?
So,
It is already preset. It's based on the character of those electron shells. Yes,
so
Shaheen?
why is it the same if it is a different electron, it has different energy, so the energy level is different, right?
So when I say the same, I mean if you go from L to K, will that ever change?
Oh, I
Will
see.
the energy ever
From
change?
one level to the other is always the same.
Correct. If I go from M to K, will that ever change?
No.
Right? If I go from P to K, will that difference ever change? So it is characteristic. If I see a 57 keV photon, I know it came from L to K. Right? If I see a 69 keV photon, right, then it came from N to K. Right? So it is characteristic. It is preset, right?